So I'm trying to kind of bring everything back to where we started. I think we do have a question. Is Simpson's paradox something that we'll be covering in today's class? Yes, it is different, but I'm pretty sure I'm the right one. Simpson's paradox, I actually don't even know what that is. I bet it's one of those cases that I do know what it is, but I've never heard the name. So that would be my guess, to be perfectly honest. So now going back into our slides. So at the very beginning of this statistics in R classes, we went over null and alternative hypothesis. Again, null hypothesis is our default. We assume that that is true until proven otherwise. So the null hypothesis for our correlation coefficient, if we are finding or trying to decide statistical significance, that means that we are assuming until proven otherwise that the correlation coefficient is not significantly different than 0. So the null hypothesis is basically the correlation coefficient equals 0, because 0 means no relationship. Until proven otherwise, we assume that there isn't a relationship. Now, if we are testing whether the correlation coefficient is significantly different than 0. If we find a p-value that's less than 0.05, then we can assume, if we have met all the assumptions for the model, that the correlation coefficient does not equal 0. So we can assume that if we have a p-value less than 0.05. So significance testing. You probably were thinking when we were back at t-test, why are you going over this? It's not actually useful in real life situations. Here we are. We're back to the t-statistic. So for this particular type of test, there usually is a different formula for each type of test. This is the t-statistic formula. So we have our correlation coefficient divided by the square root of n minus 2. And then down here, our denominator is 1 minus r squared, and we find the square root of that. So when we look at, there are several different distributions. So binomial distribution looks at like 0, 1 variables, or yes or no. The t-distribution is another type of distribution. The f distribution that we've seen before as well. They are in chi-square distribution. They all look different on the back end. So statisticians who made these tests a long time ago looked at the relationship and with statistical testing and what those actual values looked like when they're graphed out. There's a lot of math behind that, but this is following the same distribution as our t-tests. So we can evaluate it in the same way. That's what actually matters. So we can evaluate significance for correlation coefficient when we calculate the t in the same way that we can decide that information with a t-test. So this gives us a t-statistic. I'm going to go in real quick. I should have brought this up, but I do think it's a good thing to see. You'll remember a long time ago that I showed you something that looks like this. So this is looking at the t-statistic. It takes into account our degrees of freedom, whatever significance level we want, and our t-statistic that comes out of our model. So these are the different t-statistics. These are the degrees of freedom, and these are the significance level. So basically, these are cutoffs. I showed this a long time ago, but I'm trying to reiterate that the evaluation of this is the same. So if this t-statistic, you say look it up on that table or find it in R, if it's past that cutoff that's in the middle of the table, then it is significant. And R will give you a very specific significance level. I don't recommend using that table because it's not exact, but it's good for demonstration purposes. So if this t-statistic hits that cutoff, and if you want to know more about that, look at previous videos. we can find whether it's significant. The p-value is less than 0.05 or above 0.05. A word of caution, though, especially with correlation, because I find that even weak correlations sometimes have significant results, meaning there is a relationship and it's statistically significant, but it's often not meaningful in practice. What do I mean by that? So even if there is a relationship, the strength of the relationship matters. So this is going to depend on your domain and how similar values usually look. I did read when I was doing research for this class, I found an interesting statistic that in social sciences, so like public health, anthropology, psychology, often correlations that actually did have a meaningful relationship were around 0.6. In agriculture, we often saw that it was 0.7. So it just depends on the domain, and that's something you're going to have to learn based on where you are. How much are values usually related? But in those cases, statistical significance cutoff would likely have been a lot lower than that. So you have to keep in mind significance versus what you're going to have to make that judgment based on what you know about the domain or what you're studying. So that's not an easy thing to answer because there's no cutoff. So basically, what is the cutoff that you want to find? The cutoff that is actually going to add information to whatever project you're doing. Looking at questions. So I can address that, the Simpsons paradox, later. Okay, so significance testing, and we've already talked about this, but just to add a little bit more information, we find that t-statistic and our significance, as we saw in the table, depends on the t-statistic and the degrees of freedom. Degrees of freedom are calculated differently for every test that you do, but they always have, in some way, a sample size involved in calculating them. In this case, the formula is the number of data points minus 2. So that is taken into account. That's why the table isn't ideal, because your number of observations usually won't exactly be written on the table. So I recommend using R. So then you can use R or the table to find those values. Okay, one more thing before I go on to the example. I talked about this. Correlation does not equal causation. Correlation means there is a relationship, or one is associated with another. Another way to say it is that one varies in the same way as the other one varies. These are real examples of news articles that came out. It was a while ago. I think it was in the 90s or the 80s. And and this one looks like it was a little bit later. So news reporters that didn't know how to use statistics actually reported these numbers. I'm going to blow this up a little because these are the actual original things that they reported. So in this case, someone was saying, I mean, very seriously, that ice cream sales caused the murder rate to be higher in New York City. Now, in reality, this is actually, when I was learning this the first time, this is the example that was used in my class to demonstrate correlation does not equal causation. So in general, the murder rate in New York City goes up during the summer. Why? Because people are outside more often. When it's 10 degrees outside, nobody wants to be outside. So in general, that would be my guess. I don't know that for sure. But I have heard from police, just in general, I've read that when it's really, really cold, murder rates go down because nobody wants to go outside, which is interesting. But anyway, the murder rate goes up in the summer. Ice cream sales go up in the summer as well. Do ice cream sales cause the murder rate to be higher? No, they do not. And anybody who has common sense would know that. This person should have lost their job for that. So there was a similar one. Some other reporter also reported this, that ice cream sales cause drowning deaths to be higher. So they had this graph showing the different months of the year, and that as drowning deaths go up, ice cream sales go up. So one must cause the other, right? No. I'm sure you can see, drowning deaths go up when people swim, and ice cream sales, because it's warm out, go up as well. One does not cause the other. And these are real examples of things that people tried to tell you in the news. This is a great example. Do not trust statistics in the news unless they tell you details on how it's calculated. Don't trust statistics without evaluating the methods yourself. In a lot of cases, people make mistakes, really dumb mistakes like these. So always keep that in mind. Are there any questions before I go over several examples of correlation? Okay, so this should help us understand a little bit more what's going on. So we've already loaded our linear data. So there is a function called core that you can use instead of the one that I use here. It doesn't give you as much information. It only gives, it doesn't give you a p-value, basically. So in our examples, I wanted to use a function that would show us a p-value, as well as confidence intervals and the standard error. This gives you more information in general. So that's why I'm using this, but COR can be used as well if you don't care about those things. So the first thing that I'm going to show is we're going to graph this data. So this is a scatter plot of our percent with a bachelor's degree and our life expectancy. So looking at this, this is the case where I would be very hesitant to use correlation coefficient, a Pearson's correlation, as our evaluation metric. So this is an example of that it might be misused. You're seeing that a lot of values are zero here. So a lot of counties have very few people with a bachelor's degree. So we're hitting zero a lot in that case, which can bias our model. And it doesn't look all that linear. So that's a case where you can run it, but take it with a grain of salt, unless the results are very compelling. So we're seeing here a 0.414 correlation. That's telling us that, so that is the lower level of a moderate correlation. So that's moderate, but towards the bottom of the cutoff. That, given that this data doesn't look all that linear, would mean that this probably, there's not a meaningful relationship here, but you would want to do further testing given this data. Now, life expectancy versus percent married. This is something that you could run it for, run correlation coefficient for. You might want to remove some outliers, but this looks pretty linear. We are looking, and the dispersion isn't all that bad. So we're seeing this here. I would feel comfortable making assumptions based on our results in that case. That's why you always graph first. So we're seeing here also a 0.41 correlation between the percent married and the life expectancy. So there is a low level relationship here. A 0.4 in a lot of cases, like I said, social sciences tend to be 0.6 shows a pretty a substantial relationship. This, you can see, is significant, but I wouldn't call this meaningful. So that's a great example. This doesn't really give us any valuable information. Yeah, there's an association, but it's not all that strong. So that in itself does give us information. So another example. This again looks pretty linear. I would feel comfortable using this. It's a little, it has heteroscedasticity to some extent. So you would want to maybe use a rank correlation. I would probably run both and see how they differ. So running that correlation test, we're seeing a negative 0.66 correlation between the percent below poverty line and life expectancy. Now, given I have a background in social sciences, and if you read anything, you're going to know that there is a relationship between these two variables. It's pretty documented. People have tested it in many ways. The data looks okay, even though it has heteroscedasticity. I would feel comfortable using these results because of all of the other testing that they've done on these two metrics. They're very highly related. And without looking at correlation, they've done more robust statistical tests. So given my domain knowledge, even though the data is for heteroscedasticity, I would feel comfortable using these results. I'm trying to go through my thought process and what it would look like in a business case, because these are not business related, but they should be looked at in the same way. Last one we're going to look at is the percent uninsured. So that's percent that don't have health insurance. So again, we're seeing something that's pretty linear. If I were going to go through, I would want to remove some outliers. We're not going to go into that except for in linear regression, just for time reasons. We're running this. We're seeing a negative 0.44 correlation coefficient. So I would assume there's a low-level relationship here. It might not be meaningful in practice. There might be other factors that are more important.